Welcome to what I like to call the Olympic decathlon of Cambridge physics exam strategy. Why a decathlon? Well, because to achieve top marks in Syllabus 9702, or even if you're building your foundational knowledge in 0625, 0651, 0652, or 5504, you absolutely have to master multiple disciplines all at the exact same time. It is never just about memorizing facts from a textbook, it's about deep data analysis. It's about applying abstract concepts to totally unfamiliar scenarios, and it's about perfectly executing your mathematical methodology under immense time pressure. Imagine you're sitting in that exam hall. The clock is ticking down, and you turn the page to face a massive multi-part past paper question on the photoelectric effect. Let me tell you about two typical students taking this exam, who we'll call Alex and Sam. Now, Alex's exam paper is an absolute bloodbath of red pen marks from the examiner. Why? Because Alex panicked and overloaded his response with every single raw physics fact he could think of, but he included absolutely zero structural analysis. It's just a brain dump. Then we have Sam. Sam's response is also bleeding red ink, but for a totally different reason. Sam rushed the question and completely missed the specific requirements of the command words in the prompt. Throughout this explainer, we're going to fix Alex and Sam's mistakes. We are going to transform those painful red crosses into beautiful green check marks, and I am going to hand you the exact step-by-step blueprint to make sure you never make these critical errors in your own examinations. We're going to deconstruct the exact physics, the exact strategy, and the exact mindset you need to absolutely dominate this topic.
Now, you might be wondering why we are focusing so intensely on the photoelectric effect today. It's simple. You literally cannot avoid this topic. The principal examiner reports make it abundantly clear. This topic is an absolute staple. It shows up in every single examination series without fail. It is the fundamental bridge between classical wave theory and modern quantum mechanics, and let me tell you, Cambridge absolutely loves to test if you actually understand that massive conceptual leap. When our student Alex saw this topic on his paper, he just wrote down every single random thing he knew about photons. He wasted 5 crucial minutes of exam time, filled up a whole page, and scored exactly 1 mark out of 4. Painful, right? And Sam? Well, Sam tried to take a shortcut. Sam gave a vague one-sentence definition of threshold frequency that completely ignored the specific context of the zinc plate that was explicitly mentioned in the question. Both of these approaches are guaranteed to result in failure at the highest grade boundaries. What we need to do instead is look precisely at the demands of the examination and calibrate our responses to match the marking scheme, point by agonizing point. We aren't just learning physics today, we are learning the actual psychology of the Cambridge examiner. We are learning how to give them exactly what they want so they have no choice but to award you full marks. So here is our roadmap for this explainer. We're starting with the core principles to build our theoretical architecture. Then we'll move into the method mark strategy, which is all about technical methodology. After that, we'll dive into our deconstruct, solve, evaluate framework for critical analysis, and we'll wrap up with the top 3 examiner warnings straight from the source. Let's get right into it. Okay, Section 1, Core Principles and Building That Theoretical Architecture. You simply cannot construct a high-scoring, nuanced answer on a shaky foundation. In this section, we're going to reveal our very first golden rule for exam success, command word decoding. Whether the paper says state, explain, calculate, or deduce, your brain needs to instantly, automatically select the right toolkit. If you treat an explain question like a state question, you are throwing marks away. We are also going to introduce the PEEL framework, which stands for point, evidence, explanation, link. This is exactly how top-tier, A-star students structure their descriptive physics answers to ensure they don't miss a single beat. Let's look at the absolute mathematical heart of this topic. This isn't just a formula, it's a beautifully intricate network of precise definitions and causal links. This is Einstein's famous photoelectric equation, HF equals phi plus 1/2 mv squared. Let's break that down conversationally. The HF part, that is the total energy of the incoming incident photon, where h is Planck's constant and f is the frequency of that light. Phi represents the work function, which is the absolute bare minimum energy required to liberate an electron from the surface of the metal. You can think of it like an exit fee the electron has to pay to leave the material. And that 1/2 mv squared at the end, that is the maximum kinetic energy of the emitted photoelectron as it flies away. But here is exactly where students like Alex fail over and over. The examiner doesn't just want you to state what the letters mean like a robot. They want you to explain the conservation of energy that's actually happening here. They want you to use that PEEL framework we mentioned. Your point is that energy is strictly conserved in this quantum interaction. Your evidence is that the photon's energy transfers completely, all at once, to a single specific electron. 1 photon, 1 electron. Your explanation is that some of that energy is used to overcome the work function, to pay that exit fee, and whatever energy is left over becomes the kinetic energy of the electron. And finally, your link ties it all back to the core concept, explaining why simply changing the intensity or brightness of the light doesn't increase the maximum kinetic energy. A classic Cambridge trap. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's think deeply about this equation again. Notice the interconnectedness of these variables. If you increase the frequency f, and you know that the work function phi is a strict constant for that specific metal, then the maximum kinetic energy absolutely must increase in a linear fashion. This isn't just basic algebra you're doing, this is the physical reality of the quantum world manifesting right there on your exam paper. You have to see the physics behind the math.
As we analyze this further, it's clear that top-performing students don't just memorize the equation and hope for the best. They exhibit a deeply connected, conceptual understanding that easily transfers to other areas of the syllabus. Cambridge assessment objectives are designed to target very distinct cognitive domains. Assessment Objective 1 is your basic knowledge and understanding. Can you accurately define the term work function from memory? Assessment Objective 2 pushes further into application. Can you use Einstein's equation to find the stopping potential of a completely new hypothetical metal that you've never studied before? And then Assessment Objective 3 is the ultimate test of analysis. Can you look at a raw graph of kinetic energy plotted against frequency and deduce Planck's constant just by calculating the gradient? When you face an unfamiliar context on the exam, like a photocell being used in a burglar alarm system or the mechanics of a spacecraft's solar cell, you absolutely cannot panic. The physics hasn't magically changed. The foundational architecture of the equation remains completely identical. You just have to stay calm, decode the scenario, and cross-reference this topic with your knowledge of electric fields or waves to secure those top-tier marks. It's a puzzle, and you already have all the pieces.
So why do students find the distinction between key terminology so incredibly hard? This is a vital question we must ask ourselves before we look at how to actually score those marks. Think back to our student Sam. Why did Sam lose crucial marks here? Because Sam completely confused threshold frequency with work function. Yes, they are deeply related concepts, but they are entirely distinct physical quantities. Work function is a specific amount of energy. It's measured in joules or electron volts. Threshold frequency, on the other hand, is a rate. It's measured in hertz. It is the absolute minimum frequency of incident electromagnetic radiation required to cause the emission of photoelectrons, period. When you blur the lines between these terms in your written answers, the examiner immediately knows you lack precision. And in Cambridge physics, precision is quite literally your currency. Every single time you write a vague or interchangeable term, I want you to imagine a red pen violently striking through your mark. We need to eliminate that ambiguity entirely, and to do that, we need a rigorous, bulletproof system for putting our thoughts onto the paper.
That brings us right into Section 2, the method mark strategy. This is our technical methodology for exam success. The crucial point here is how we shift from simply knowing the theory in our heads to actually proving it to the examiner on the page. This is where we see the real transformation happen. We are moving from raw, unstructured knowledge into what I call the physics success blueprint. In Cambridge physics, your step-by-step procedure is just as critical as your final numerical results. Let me tell you a little insider secret directly from the grading rooms. Examiners actually want to give you marks. They really do, but they can only award points for what is mathematically and logically demonstrated right there on the page. Think about those massive, multi-step photoelectric effect calculations. They are often worth 3, 4, or even 5 marks. But did you know that the final answer itself is usually only worth 1 single mark? That's your A1, or accuracy mark. The rest of those points are C1 or M1 marks, compensationary and method marks. If you just mentally punch numbers into your calculator, make a tiny accidental rounding error, and just write down the wrong final answer without showing any of your steps, you get a 0, nothing. But if you clearly state the rearranged equation, show the substitution of the values with their correct SI units, and then make that same silly calculation error at the very end, you might still walk away with an easy 3 out of 4 marks. This strategy of showing your work isn't just a suggestion, it is absolutely non-negotiable if you want an A-star. Let's walk through this standardized 5-step sequence together. By following these exact steps, you ensure that you are picking up every single available method mark along the way. Step 1, identify key elements and extract the data. If the question gives you the wavelength of light instead of the frequency, don't just hold that in your head. Immediately write down the symbol for wavelength, write equals, write the given value, and then explicitly recall the wave speed equation, C equals F lambda, to calculate your frequency. Step 2, apply the relevant principles. Literally write the photoelectric equation clearly on the page. Show the examiner you know the starting point. Step 3, execute the analysis with incredibly clear notation. Do not skip steps. If you are converting from electron volts to joules, physically write out the multiplication by 1.6 times 10 to the negative 19 on the paper so the examiner sees exactly what you're doing. Step 4. Verify your results. Does an electron velocity of 3 times 10 to the 8 meters per second make sense? Absolutely not, because that matches the speed of light. It means you probably forgot to square root your velocity squared value at the end of the calculation. Always, always check for reasonableness. Step 5. Present in the appropriate format. Significant figures heavily matter here. If the raw data in the prompt is given to 2 significant figures, your final answer should generally be to 2 or at most 3. Imagine you had 60 seconds to rewrite Alex's chaotic, brain dump answer using this exact 5-step framework. By simply structuring the math vertically down the page, step by step, and defining every variable, Alex's score instantly jumps from a miserable 1 out of 4 to a perfect 4 out of 4. That is the power of methodology.
Now let's transition into section 3, deconstruct, solve, evaluate. This is the specific critical analysis framework that will help you tackle the absolute most complex, unfamiliar contexts they can throw at you. Get your mental gears turning because we are about to test your real-time problem-solving skills in an interactive workshop.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, now that you're an official part of the community, let's step right into our interactive workshop. This deconstruct, solve, evaluate mantra is your ultimate problem-solving toolkit for heavy data interpretation and drawing solid evidence-based conclusions. We are jumping into Challenge 1, the data scan. I want you to vividly imagine a complex photoelectric graph. We've got stopping potential on the y-axis and frequency of the incident light on the x-axis. We're on a 60-second mental countdown timer. Your challenge is to extract the core trend. What does the x-intercept represent on this graph? What does the gradient, the slope of the line, actually represent? If you use the deconstruct step properly, you mentally map the visual graph directly to Einstein's equation. The equation incorporates the maximum kinetic energy, which is directly linked to stopping potential. If you rearrange the photoelectric equation to solve for the y-axis variable, stopping potential, it perfectly matches the universal format of a straight line graph, y equals mx plus c. Boom. Just like that, in under 60 seconds, you've deduced that the gradient relates to Planck's constant divided by the electron charge, and the x-intercept is precisely the threshold frequency. That right there is how a top-tier decathlon-winning student extracts data and solves systematically.
Now let's look at descriptive answers. The contrast here is incredibly stark. The classic mistake students make is providing a generic textbook response, whereas examiners rigorously demand that you link every single point to the specific scenario given in the prompt. Welcome to Challenge 2. Find the flaw. I am going to read a flawed sample paragraph, and I want you to identify exactly where the marks are being lost. Listen closely. Here's the answer. The photoelectric effect shows light is a particle because increasing intensity doesn't increase the energy of the electrons, but increasing frequency does. Got it? Let's break it down. Did you spot the major flaw? The answer is entirely generic. It sounds like it was copy-pasted from a revision guide. A context-specific answer, one that actually gains the marks, must refer to the specific scenario. It should sound more like this. For the illuminated zinc plate provided in the experiment, increasing the intensity of the UV light increases the total number of photoelectrons emitted per second, but the maximum kinetic energy of these electrons remains perfectly constant. Only by increasing the frequency of the UV source beyond the zinc-specific threshold frequency will the maximum kinetic energy of the emitted photoelectrons actually increase. Do you hear the massive difference there? The context-specific answer uses the exact terminology, it references the specific metal, zinc, and it perfectly clarifies the vital difference between the number of electrons and the energy of those electrons. When an exam question explicitly asks for a comparative analysis, you must hit all 4 of these specific targets to extract the maximum available marks. This brings us to Challenge 3, speed writing. You've got 30 seconds on the mental clock to think of a perfect Peel paragraph, comparing the classical wave theory of light against the modern particulate theory of light, specifically in the context of the photoelectric effect. Think about it. Classical wave theory suggests that energy should accumulate over time, meaning that even a very low-frequency, dim light should eventually deliver enough energy to eject an electron if you just wait long enough. But the evidence, RE, in the Peel framework shows that electron emission is completely instantaneous, thereby proving the particulate nature of light where a single photon interacts with a single electron in a one-to-one exchange. To write this perfectly, you must use strong comparative connectives like whereas, conversely, or indirect contrast to.
You provide the hard evidence of instantaneous emission, and you conclude that the photon model is the absolute only mathematically and physically sound explanation for the existence of a threshold frequency. Master this comparative structure, and you will completely master the conceptual high-mark essay questions.
Let's move into Section 4, our final act. Now for the absolute most valuable part of our explainer, the insider alerts directly from the principal examiner reports detailing exactly where students lose marks year after year. We are establishing the final system here. We are going to look at the 3 critical rules that guarantee top marks, summarizing our command word decoding, our PL framework, and our time management matrix. Let's look closely at the pitfalls that trip up thousands of students globally.
Take a very close look at these top 3 mistakes, because completely avoiding them is the absolute fastest way to elevate your grade boundary. Mistake number 1, vague answers. Saying something like, "the energy changes," is totally meaningless in physics. You must be precise. You must say the maximum kinetic energy of the emitted photoelectron increases. Every word matters. Mistake number 2, forgetting to check format and presentation. This means forgetting your units or messing up your standard form. Leaving an answer simply as 4.5 instead of 4.5 electron volts or 4.5 times 10 to the negative 19 joules will cost you the final accuracy mark every single time you do it. It also means poor, messy handwriting where the examiner literally cannot distinguish between your letter V for velocity and your Greek letter nu or F for frequency. If they can't read it, they can't grade it. Mistake number 3, which we explored deeply just a moment ago, is ignoring the context. If the question involves an accelerating voltage used to stop the electrons in a vacuum tube, you must explicitly relate your kinetic energy calculation to the electrical work done using the specific voltage provided. When you rigorously eliminate these 3 exact errors from your exam technique, you essentially build an impenetrable fortress around your grade. Your mark potential is rapidly approaching 100%.
I highly recommend using a memory hack to permanently lock in the key variables, ensuring your terminology is always precise, crystal clear, and ready to deploy at a moment's notice. Think of the acronym IFED: intensity, frequency, energy, work function. Intensity affects the number of electrons emitted. Frequency affects the maximum kinetic energy of those electrons. Energy is always conserved. Work function is a strict constant for the specific metal. Recalling IFED during a high-stress, high-pressure exam scenario ensures you will never, ever confuse your variables again. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. The difference between an A grade and a C grade isn't usually raw intelligence, it is tactical execution. It is the ability to read the matrix of the exam paper and give the examiner exactly what the marking scheme demands, using the structured frameworks we've heavily discussed today. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
So, as we wrap up this explainer, I challenge you. Take this strategy, pull up a past paper today, practice it, and see the immediate difference it makes in your results. Theory without application is just trivia, guys. You now have the theoretical architecture, you have the method mark strategy, and you know exactly which examiner warnings to avoid. The ball is entirely in your court now. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep solving. But I'll leave you with this final thought to ponder. If Einstein's incredibly simple equation, hf equals phi plus ke, was enough to completely shatter centuries of established classical wave theory, what other established facts in the universe are just waiting to be disproven by the next generation of physicists? Maybe it'll be one of you. Until next time, stay curious and keep pushing those boundaries.